Hey Trig, here is our last section on in chapter 4. We are going to talk about an application of sine and cosine curve graphing. It's called simple harmonic motion. Those of you that had physics may have had this equation before, but the position of a point oscillating about an equilibrium position at time t is modeled either by cosine or sine, depending on where you start. Okay. If you notice, you know how cosine starts at 0, 1 and sine starts at 0, 0. Well, if you start somewhere other than the equilibrium point, then you're going to model it by cosine. But if you start right at an equilibrium point, then you model it by sine. The A is the amplitude. As you see here, the amplitude of the motion is the absolute value of A, just like it is when we talked about the graph. Omega is the angle, okay? So we'll talk about that in a minute. So they're using that instead of theta is all, okay? T is the time, if it's, how many, if it's seconds, minutes, etc. Okay? The period is 2 pi divided by omega. Well, wasn't in our equations, we had A times the cosine of bx plus c or whatever, and we took our period was 2 pi divided by the number in front of x. Well, it's the same here. The period is 2 pi divided by the number in front of t. Okay, we're using t instead of x, okay, because this is modeled over time. The frequency is just the reciprocal of the period. That's how many oscillations per second. How many times is it going through up, down, and back per second? How many times is it doing that? Okay, so let me give you an example here. I do want to show you this quick video. All right. Okay, so that's just I'm going to use our own paper here. Okay, I just wanted you to kind of see it in a little video, so you can instead of just looking at this picture. But what we're going to do is model some different things using the idea of simple harmonic motion. Suppose the object attached to a spring is pulled down 5 inches from its equilibrium and then released, and the time it takes to complete one oscillation. By oscillation, it means, you know, just like a sine curve. Okay, it's an oscillation is how long it takes to go up, down, and back to beginning. Okay, or in this case, up and through and back to the beginning. Okay, so it takes one oscillation takes 4 seconds. So let's think about it. We want to, I'm just going back. I just put this back up. We're still using the problem I put on the previous page. Okay. We want an equation that models the position of the object at any time. Okay. So because I gave this little hint here. Okay. If the object starts at equilibrium point when time is 0, then you use sine. This was pulled down first and then released. Okay, so we're going to use cosine. That's how you decide whether to use sine or cosine. If something just starts at equilibrium, we use sine. If we pull something down, like it was in the video or like it is in this example, then we use cosine. So I know I'm going to use A cosine omega t. I know I'm going to do that. I need to figure out my angle. Okay, so I'm going to use the fact that it takes 4 seconds to go 2 pi. That's what they told me, right? It takes 4 seconds to complete one oscillation. That's 2 pi, all right? So since it takes 4 seconds to go 2 pi, then omega is 2 pi over 4. 2 pi over 4. Is that okay? That's how many radians in 4 seconds. It takes 2 pi. It takes 4 seconds to go 2 pi. So it's taking pi over 2 is our omega. Okay, you'll get used to this. All right, my amplitude was 5. They said I pulled it down 5 units and then let go. Okay, so my A is 5. And since I pulled it down, I'm going to use -5. And then cosine omega t. I got it. Give an equation that models the position of the object at time t. You tell me how long, and I'll tell you where the position is in this going back and forth. I pulled it down 5. I let go. It goes up. Okay, back down, right? It goes past 0, up to 5, back to 0, back down to 5. Is that okay? And it takes 4 seconds to do that. 4 seconds to go 1 period. Determine the position at 1.5 seconds. Well, then I'll put 1.5 in for t. -5 cosine of pi over 2 times 1.5. Making sure I'm in radians. I do that and I get 3.54 inches. That's where it is. It's at 3.54 inches after 1.5 seconds. So that means it went past 0 and it's up at 3.54. Okay. It's going to go up to 5, back down to 0, and back down to -5. Okay. Where'd I get the inches? Right here. It said it was pulled down 5 inches from its equilibrium and then released. The time it takes is 4 seconds. Okay, find the frequency. Well, the frequency is just the flip of the period. So since it's the reciprocal of the period, so 1/4 oscillations per second. I don't know if you got that the period was 4. The period is how long does it take to do one cycle, right? It takes 4 seconds to go. They told me the period was 4 from the very beginning. How long does it take to complete one oscillation? 4 seconds. That's my period. The period is 2 pi over omega. 2 pi over 2 would be 4. That's another way you could have figured out omega. They told me the period was 4. So therefore, the frequency is 1/4. So again, I like this example for you to get what all these things mean, okay, in the context of the equation. Okay, so all we knew was to pull down 5 seconds, and it takes pull down 5 inches, and then let go, and it takes 4 seconds to get back down to that spot. Okay, since I pulled it down and then let it go, it wasn't starting at equilibrium, so it was -5 cosine of what? I needed to find my omega. I either used that the period was 4, And I could have actually done it that way. I knew from as soon as it told me it takes 4 seconds to make one oscillation, I know the period is 4. So I could have found the frequency right away as 1/4. Period and frequency are flipped. It's 1/4 oscillation per second. I could have gone, since the period was 4, I could say 4 equals 2 pi over omega. Multiply both sides by omega. Divide by 4. And then I got my pi over 2 for my omega. Now, the way I did it here was I just kind of did the divide by 4 right away. But that's kind of where it comes from. Okay? So oftentimes in your homework, I'm just going to give you the equation. Okay? Or the book. The problems already have the equation there. They say, hey, an object oscillates according to this model. Analyze the motion. That means tell me the period, tell me the frequency, basically what that's saying, okay? The object oscillates 8 feet in either direction from its starting point. I know that from the number 8, okay? It starts somewhere, it goes up 8, down 8, and back to the beginning. Now, it doesn't go horizontally like that, but it goes just up, down, back. Or it goes to the right, back, and back. Okay, it's either going vertically, it's a spring, or it's going horizontally. But I know it moves to the right first or up first. Unlike the last one that was pulled down first. Okay, this wasn't pulled, it just starts. Maybe it's just clicked on it's electric. And I turn it on and all of a sudden it goes 8, -8, back to 0. Or I turn it on, it goes up 8, down to -8, back to 0. So the object oscillates 8 feet in either direction from its starting point. The period is 2 pi over 3. I put that as 2.1 just to give me a number that goes with that, okay? The frequency, I flip it upside down, okay? So this is saying it takes 2.1 seconds to go up 8, down 8, back to 0. Okay, that's what it's telling me. Because I know t was measured in seconds and s of t is measured in feet. Okay, so it tells me that. So the object oscillates 8 feet in either direction. The period is 2.1 seconds. That means it takes 2.1 seconds to go through an entire cycle, up, down, back. That's what the period means. The frequency, I'll flip the period. It takes about it goes through about a half an oscillation per second, 0.48 oscillations per second. That's what the frequency is, okay? So when you see analyze the motion, that's what we want to say. Okay, damped oscillatory motion is just something we're not going to do. I wanted to show it to you though. We aren't going to do it, but I want you to understand what that word damp means. I just think of shock absorbers. All right, when you go, how you hit a bump and your car doesn't constantly keep going up and down forever. It gets slower and slower. And it's actually damped by the exponential function e. Isn't that cool? We're using exponential function and trig in the same equation. That's cool. Okay, there is such a thing as damped oscillatory motion. We're looking at simple harmonic motion, okay? Which isn't really, like most things do, slow down over time, right? Doesn't constantly go in that direction, but anyway, a weight is attached to a spring pulled down 2 inches below equilibrium. They want us to write the equation. Assuming that the period is 1/3 of a second, determine the model that gives a position. And what's the frequency? Well, the frequency is the flip of the period. So I flip 1/3, I get 3 cycles per second. That's what the frequency is. It goes through 3 cycles, or the frequency, 3 cycles per second. Okay. The period is 1/3 of a second. It takes 1/3 of a second to get through a cycle. 1/3 of a second, and I'm through up, down, and back. Okay. So I need to find omega. So since I knew the period is 1/3 and the period equals 2 pi over omega, I find omega to be 6 pi, and then I have my equation. Okay, your homework